Casting Alloys for Metallic Restorations, Chapter 3, Section 3, page number 183. Lost wax casting. The basic principles are simple. A wax model is produced of the desired shape, and this model is invested in a material resistant to high temperatures. The wax is then removed by melting and burning, leaving behind the cavity of the desired shape. This can now be filled with molten metal, so that the metal assumes the shape of the original wax carving. The stages in the production of a dental casting are these: preparation of the dentition, production of an impression, pouring of a model, waxing of the desired shape, investing the wax pattern, burnout and heating, melting and casting the alloy, finishing and polishing, and finally the heat treatment. Clinical significance. It is the dentist's responsibility to know what metals they are providing for their patients. This requires a knowledge of the types of alloys available and their composition and properties. Desirable properties. The choice of alloy is governed by a number of factors. Cost is a serious consideration, due to the increased price of gold today. Other considerations are the biocompatibility of the alloy and its resistance to corrosion and tarnish. It is these factors that particularly limit the range of alloys available for dental applications. Suitability for a specific application, be it a low-stress bearing inlay or a posterior bridge, is determined primarily by the mechanical properties of the alloy, such as its stiffness, strength, ductility, and hardness. Stiffness is a consequence both of design and of the elastic modulus of the alloy. The higher the elastic modulus, the stiffer the structure will be for the same shape. This is an important consideration, especially for long-span bridges, cast posts, partial dentures, and dentures clasps. These restorations are also likely to be subjected to fairly high loads and therefore need to be resistant to permanent deformation. This requires the alloy to have high yield stress or proof stress. However, for such things as clasps, high strengths need to be balanced against ductility, since it is important that the alloy is not so brittle as to fracture when small adjustments are made. Main alloys used in dentistry. We have noble and precious alloys, and we have base metals alloys such as nickel and cobalt-based alloys and titanium. Noble and precious metal alloys, they consist of 8 elements, and they are corrosion resistant, and that makes them noble, expensive, and that makes them precious. Noble, such as gold, platinum, rhodium, ruthenium, iridium, and osmium, and the precious such as silver and palladium. High gold alloys. This is a group of alloys that have been around for some considerable time, and that can be distinguished from other alloys used in dentistry by their high precious metal content, which must not be less than 75%, and a gold content in excess of 60%. The precious metal content is usually made up of gold, silver, platinum, and palladium, and these alloys can be classified into 4 distinct groups. As you can see, we have 4 types of high gold alloys: soft, medium, hard, and extra hard. The soft has 80 to 90% of gold, the medium has 75 to 78% of gold, the hard has 62 to 78% of gold, and the extra hard has 60 to 70% of gold. The amount of gold in an alloy is defined in one of 2 ways. 1. Carat. Pure gold has a carat value of 24, and fineness. Pure gold has a fineness rating of 1000. Alloying elements in dental gold alloys. The largest fraction by far of these alloys is gold, with lower amounts of silver and copper. Some formulations also contain very small amounts of platinum, palladium, and zinc. The copper is a very important component, as it increases the strength, particularly of the type 3 and type 4 gold alloys, and it reduces the melting temperature. The limit to the amount of copper that can be added is 16%, as amounts in excess of this tend to cause the alloys to tarnish. A variety of other elements such as iridium or ruthenium, they may be present. These have very high melting temperatures and act as a nucleating sites during solidification, and this helps to produce a fine grain size. The silver has a slight strengthening effect and counteracts the reddish tint of the copper. The platinum and palladium, they both increase the strength and the melting temperature. Zinc acts as a scavenger during casting, preventing oxidation, and improves the castability. Strengthening mechanism. Although all of the alloying elements give rise to some increase in the yield strength of the gold alloy by forming a solid solution, the most effective strengthening mechanism is the addition of copper, in what is known as order hardening. This heat treatment is carried out after the homogenizing anneal at approximately 700 Celsius, which is preformed to ensure a uniform composition throughout the casting. It involves reheating the alloy to 400 Celsius and holding it at that temperature for approximately 30 minutes. Rather than being randomly distributed, the copper atoms arrange themselves in little ordered clusters. This ordered structure prevents slippage of the atomic layer, which has the effect of raising the yield stress and the hardness of the alloy. There must be at least 11% copper in the gold alloys for order hardening to occur, so it cannot occur in type 1 and type 2 gold alloys. Type 3 gold alloys have just enough copper, and a small improvement in strength is observed. For type 4 gold alloys, the improvement in strength is quite significant. Self-hardening. It is to allow the alloy to cool slowly on the bench rather than quenching it immediately on casting. But it has a disadvantage. It has the disadvantage of not being as well controlled as when the alloy is first given a homogenizing anneal and then a hardening heat treatment. Other features for high gold alloys: they are easy to cast and produce. Homogenizing anneal is desirable for the type 3 and type 4 gold alloys. They have low casting temperatures, and the casting shrinkage 1.4 use of a gypsum bonded investment. Also, low Vickers hardness values, easy to polish to a smooth surface finish. They have good quality, well-fitting castings. Tarnish resistance is excellent, and excellent biocompatibility. High gold alloys applications. Given their different mechanical properties, the recommended applications for the use of these alloys is as follows. Type 1. These are the best used for single surface inlays in low stress situations, as they are relatively soft and easily deformed. They need plenty of support to prevent deformation under occlusal loading. The low yield stress of these alloys allows the margins to be burnished easily. Given the high ductility, they are unlikely to fracture. Type 2 alloys. These can be used for most inlays. However, those within sections should be avoided, as deformation is still a possibility. Type 3 alloys. These can be used for all inlays, onlays, full coverage, crowns, and short span bridges. Cast posts and cores because of their great strength compared with type 1 and type 2 alloys. However, they will be more difficult to burnish and have a higher potential for localized fracture if they are burnished excessively. Type 4 alloys. These are used for cast posts and cores and long span bridges and in partial denture construction, particularly clasp arms. Clasp arms can be adjusted in an as cast state and then heat hardened. Of course, this will not be possible when using a self-hardening alloy. The low elastic modules and high yield strength of the gold alloys provide a high degree of flexibility to clasp arms, which allows them to be withdrawn over quite severe undercuts without danger of permanent deformation. These alloys cannot be burnished in their hardened state and are therefore unsuitable for inlays. High gold alloys applications. We have type 2, type 3, and type 4. Type 2 is mostly inlays. Type 3 is inlays, onlays, crowns, short span bridges, cast posts, and cores. And type 4, cast posts and cores, long span bridges, and partial denture. Medium and low gold alloys. The rapid rise in the prices of noble metals in the 1970s stimulated manufacturers to produce many new alloys with reduced gold content. Some of these may be classed as medium gold alloys, with the gold content varying from 40 to 60%. These medium gold alloys were introduced in the early 1970s and have become very popular. The palladium and silver contents were increased to compensate for the reduced gold content, while the copper content is in the range of 10 to 15%. Palladium is added to counteract the tendency of the silver to tarnish, and the copper allows heat treatment. The low gold alloys have gold content in the range of 10 to 20%, and the silver content from 40 to 60%, and the palladium up to 40%. Semi-precious casting metals, such as silver palladium alloys, which is known as white gold. Palladium improves the resistance to corrosion and prevents tarnish. High casting temperatures for these alloys require the use of phosphate bonded. Tarnishing does occur with these alloys. Base metal alloys, which is known as low cost, such as cobalt chromium alloy. The alloy consists of cobalt, chromium, and molybdenum and titanium. They have high rigidity and yield strength. They have less casting accuracy, and the higher the chromium content, the better the corrosion resistance. Molybdenum to refine the grain size by providing more sites for crystal nucleation during the solidification process. Carbon can combine with other elements to form carbides that can raise their strength and the hardness of the alloy. Too much carbon, though, will result in brittleness. Cobalt chromium alloy properties: difficult to handle, high strength at high temperature, melting temperatures between 1300 and 1400 Celsius, casting shrinkage is at 2.0%, phosphate bonded refractory investments, accuracy is compromised at these high temperatures, the high hardness and difficult to polish mechanically, the lack of ductility will lead to clasp arm fracture. Non-precious alloys for ceramo metal restorations: high modulus of elasticity, 250 GPa, twice that of gold, clasp arms thinner in cross-section with high rigidity, density of about half that of the gold alloys, excellent history of biocompatibility. Nickel increases the ductility and reduces the hardness. Nickel is a well-known allergen. Cobalt chromium alloys: as compared to gold alloys, it is very lighter in weight, higher elastic modulus, similar corrosion resistance, and it's less expensive. The disadvantages: it has a complicated production process, high fusion temperature, requires special equipment for finishing and polishing.